In this episode of chemistry, we're going to talk about the Rutherford Bohr atom. Now sit tight, because this might be a rather boring lesson. So before we jump into it, we can talk about the electromagnetic spectrum. We know we have our long wavelength, low frequency, low energy waves on the left, like our radio waves and microwaves. And then all the way on the right, we have the short wavelength, high frequency, high energy, gamma rays and X-rays. In the middle, we have our visible light, Roy G. Biv. Light, we know, can act as a wave, but it can also act as a particle. These light particles are called photons. We can create line-emission spectrums based on the photons that are released from an atom. Atoms will give off photons when there's a change in the energy of the electrons. So electrons start off in a ground state. When you put energy into the atom, the electrons will jump up to an excited state. As they come back down from an excited state, the atom will give off photons, and that helps us create our line emission spectrum. This line emission spectrum shows us the frequency and wavelength that an atom emits when you change its energy levels.
In the last video, we talked about how Ernest Rutherford and his gold foil experiment had helped scientists discover this positive small nucleus in the center of an atom. But that didn't tell us what the electrons were doing. And he just speculated that they were moving around the nucleus almost like planets in orbit around the sun. But one of the researchers working underneath Rutherford, Niels Bohr, spotted a problem in this. He knew that any charged particle that's moving is going to be giving off electromagnetic radiation. As it does that, it's losing some of that energy, and so it's going to quickly spiral into the middle and annihilate essentially the whole atom. So he knew that wasn't right. He also knew that as it gives off radiation, the wavelength of that radiation is going to vary. And as it varies, we're going to get this nice, smooth spectrum of electromagnetic radiation given off by high-energy atoms. But when we started to look into space, what we found is that light wasn't smooth. It had these discrete units within it. And so that spectra had to be described. And Bohr's model helped to do that. And so if you think of it like this, and this works for hydrogen, is what the Bohr model is built on, you have these energy levels. And so an electron can be in energy level 1, energy level 2, energy level 3, but it can never be found in the middle. It's quantized. It has to be in one of those levels or another level. And so how does it move between levels? Well, if it absorbs energy from a photon, electromagnetic radiation, for example, it'll jump to a higher level. And as it moves down, it's going to emit those photons. And that helped to describe what we were seeing in the spectra. And so that improved our model. So we now had the cloud that had the electrons in it, and then the nucleus. And so we found these negative electrons in the cloud, and then protons and neutrons were found in the nucleus. And in a neutral atom, the number of protons and electrons are going to be equal. And the electrons tell us a lot about the properties of that atom. In fact, the whole periodic table is built on the electrons. Electrons especially we have in these outer levels. Now the Bohr model helps us explain what those electrons are doing and how they're moving. They move into these discrete energy states, and that helps us to explain the spectra.
So in Bohr's model, electrons are only allowed in fixed orbits, each with specific amounts of energy called energy levels. The energy levels closest to the nucleus have the lowest energy, and as you move away from the nucleus, the energy levels increase. So electrons can only gain or lose certain amounts of fixed energy, which we call quantized amounts of energy. And only certain photons will be produced. So Bohr stated that when an atom absorbs radiation or energy, electrons jump to the next energy level. Photons will be emitted when an electron falls from a higher energy level to a lower one. So if you go from energy level 3 to 2, you would see red photons being emitted. From 4 to 2 would be green, 5 to 2 would be blue, 6 to 2 would be violet, and that creates our line emission spectrum with the different colors.
Electrons weren't orbiting like planets. They were actually jumping between orbits, according to Niels Bohr. And so they didn't just move back and forth on all these infinite number of orbits around the nucleus, giving off a smooth amount of spectrum, almost like a ladder, that an electron could be here, but it could also be here, and it could never be found in the middle. We call that being quantized. It has to be in a specific unit to exist. Now, how do you move an electron to a farther level? Well, you have to put a little bit of energy into it. So if we add a lot of energy, we could jump it up to this energy level. And as it falls back down, it's going to release a certain amount of energy. And so this is a visual or a model of what the Bohr model might look like. And so as it orbits around the center, if it receives a photon, it jumps to a higher level. If it gives off an equal photon, it'll drop down to a lower level. And so it's only existing in these quantized orbits. And this helped to explain spectra.
Bohr created this model for a hydrogen atom. Energy of photon depends on the difference in energy levels, as we just saw. Bohr calculated energy matched the infrared, visible, and ultraviolet lines for hydrogen. So here we have low energy with the red light and higher energy with the violet light.
That they were seeing these discrete units of light. And so where was that light coming from? If you look at hydrogen, well, you can see here as we move from this energy level 2 up to energy level 3, it requires a certain amount of energy. And as the electron falls back down, it's going to give off that energy. It's going to give off that light. And so the Bohr model predicted what these numbers were, and they fit perfectly with the numbers that we were seeing in the spectra. And so again, this only works for hydrogen, and so it's a good step model, or it's a good model to get you started on understanding how the atom is really put together.
Each element has a unique bright line emission spectrum, or atomic fingerprint. For example, this is the emission spectrum for helium. Bohr's specific calculations only work for hydrogen. We can create line emission spectrums based on the photons that are released from an atom. Now, atoms will give off photons when there's a change in... My mom just sneezed. Bless you, mommy. When there's a change... Bless you, mommy. When there's a change in the energy of the electrons. So electrons start off in a ground state. When you put energy into the atom, the electrons, bless you, mommy, will jump up to an excited state. As they come back down from the excited state, the atom will give off photons, and this helps us create our line emission spectrum.